I think the title has changed slightly from what I submitted, but basically what we were trying to do was we were trying to understand the depth versus diameter function, as well as the simple to complex transition of craters on Pluto and Charon. And I mentioned that this is a statistics fantasia because we tried to explore a lot of different methods to try to do this. And the main reason for that is I didn't see Alan Stern on, so I think I can say this, that despite the tremendous success of the New Horizons mission, it is still a very limited data set when you really try to dig into this kind of analysis and when you really try to pick apart what's going on with these impact craters. And one of the issues, especially for depth versus diameter, is simply that we do not have, or we did not have, any sort of laser altimeter. So all of the topography is done through stereo reconstruction. So if I can, there we go. So the approach that we tried to do for this was we tried to first identify the best preserved craters based on how they looked. So does this look like it is a pristine crater or not? This next thing that we tried to do was we tried to identify different features that are commonly attributed to simple craters or complex craters. That would be a bowl-shaped shape. That would be a flat floor. Despite what Clark said, I think that flat floors are kind of commonly used to indicate a complex morphology, or at least transitional morphology. Whether it has a central peak, terraced walls, scalloped rims, all of these different things. Then, after we classified crater morphology, we tried to classify crater morphometry. We tried to measure crater depth. That was the easy part. The next part was the hard part, which was the analysis, and that is where the statistics fantasia comes in. So this is the kind of imagery we were looking for. This was actually pretty good imagery. This is Charon, and the crater on the left is a large crater that, to me at least, looks fairly bowl-shaped. It does definitely have floor deposits in there, but the overall shape is more bowl-shaped than it looks flat floor-shaped from a typical complex morphology you would see on the moon. The smaller crater, 12 kilometers versus 18 kilometers that you see on the right, looks more flat-floored with a possible central peak in the middle. But this crater is 5 kilometers smaller than the one on the left. And even if you're going to quibble with me that these are not what the classification is that I said they are, you could at least say there is a chance that these are classified as I have as possibly classified. And so we have a situation where we are not only we have some sort of ratty data in terms of the images and the topography, but we also have significant noise in how we classify these features. We had limited sun angle. We also had high emission angle. So you can see that the image at the right, it looks like we're sort of looking at an angle at this crater, and we are, and that's going to throw off some of the interpretation. So all of the analysis steps that we do after all of the measurement has to factor that in somehow. The depth measurement, after we did all those classifications, most people use profiles, including the last talk. We saw, I think it was 8 profiles across the crater. I actually dislike profiles personally because even if you use a lot of profiles, you're still throwing out some of that topography data. So what I try to do is I try to use all the available information, and that's shown here in sort of a multi-step process where on the left, upper left, we have the topography. This is not shaded, this is colored so that blue is low and red is high. And what this is showing you is that the code that I created, I've been working on this code for now about 13 years, it creates an annulus that identifies the rim. This is simply based on the manual identification I already did. So it puts down a possible rim. It puts down an inner 50% for a possible floor. And then it puts down a ring or a donut around the outside to try to identify a possible surrounding surface elevation. What the code does then is it searches radially from the crater center at each rim point, searching for local highs. So it does a profile, and where it finds a local high, it says that that is the probable rim at that angle from the crater center. For the surrounding surface, it takes all of those pixels that are in that donut shape, it throws out the lowest, it throws out the highest, and then it takes an average. What it also does is it also removes any overprinted craters. So there's this small crater here. I think you can see my, yeah, you can see my mouse. There's this crater here. Those pixels were automatically removed from the algorithm before it did this max-min removal and averaging. For the floor, it does a similar thing where it takes all the pixels in that circle shape and it throws out the highest ones and keeps the lowest ones. So what we're left with is shown in the upper right, where we have a rim where we have identified the highest points radially from the crater center, and we have a floor where we have the lowest points in the floor. Then it's a simple subtraction in order to give you the actual depth measurement, rim height to floor depth. There are uncertainties associated with all of these. We propagated those through, including the uncertainty in the actual elevation at every single pixel from the stereogrammetry that Paul Schenk has done. So all of this has uncertainty associated with it, and we've used now the entire crater shape to give us the depth. Now, if I can do a small aside, it was mentioned in the last talk that Pike looked at this 40 years ago. I can't believe it's actually 40 years now. 1980, this is figure 3 from his paper, where he showed the diameter along the x-axis, and he plotted about 40 craters and whether they were bowl-shaped, whether they were flat-floored, central peaks, scalloped rim, or terraced walls. And you'll recognize these features because those are the same ones that I looked at because I used this as a basis. What he showed, I think very convincingly in this deceptively simple plot, is that there is a range of onset diameter at which each of these different complex morphologies start to develop. Not only is there a range, and it's different for each one, but there is a range for each one. So you can see that it is fatter. The distribution is fatter here at about 8 to 9 kilometers for flat floors, but he found some flat-floored craters on Mars about 2.5 kilometers across. So we did the same thing. I'm going to skip that slide and just go right on to this. This is sort of a souped up version of what Pike did using modern plotting techniques. This is called a violin plot, and it's a really cool plot. I found it about a year ago, and what it does is it does that same sort of thing that Pike did, where it sort of groups the data together. So you can see that where there are more data points, we have more data at that diameter. And what it does is it draws an envelope around that to sort of give you again this idea of where most of your data lie. And yes, there are much smaller craters on Pluto and much smaller craters on Charon, but I didn't need to identify them for this study. So what this shows is a simple visual examination that there is a range of these onset diameters that varies not only based on morphology, but that varies within the morphology, that we get a few features that could be called complex morphology at much smaller sizes than where most of them actually appear. So then the question is, how do we actually analyze that? In the last talk, and what I actually did in my doctoral dissertation, we'll just say a couple years ago now, is we look at that 50% point of where do the craters become less than 50% likely that they're going to have that feature, that morphology. In this case, I tried to, again, soup it up a little bit. Instead of the 50% point, the problem with Pluto and Charon data is that while I could identify pristine craters, I couldn't always identify the morphology, or I couldn't always convince myself that, yeah, that really is a central peak in that 12-kilometer crater, or that really is a bowl shape in that 18-kilometer crater on Charon. And so what I had to do was come up with another way to deal with that uncertain data. And I'm sorry you're going to hear a car in the background, so I'm going to close a window. Sign of the times. So what I did was I created a histogram, and these are smooth histograms. It's actually a kernel density estimator. The actual terminology isn't important for this. It's effectively a smooth histogram. And I took, for example, all of my bowl-shaped craters on Pluto as a function of diameter, created a smooth histogram, and then I took all of the craters that I found on Pluto that were pristine in this sample, and I created the same thing, and I divided the two. So what you're seeing effectively in this dark mauve, perhaps, color is you are seeing a fraction of craters with this morphology as a function, as a fraction of all of the craters that were identified. So what you can see is that that 50% point for Pluto is roughly 9 kilometers or so, but it doesn't even come close to the 50% point for other features that we would commonly associate it with complex morphologies. If you were to go with that 50%, then you'd have to say that the transition diameter is somewhere between 15 and 20 kilometers, or even up to 25 kilometers for scalloped rims. So what we did was we said, we're going to consider the transition diameter based on morphology at where these curves cross. So what that means is that where this simple crater curve crosses any of these other morphologies, that is going to be the transition diameter based on that morphology. So for Charon, for example, we see this progression where it goes to progressively larger and larger crossing diameters, which means that that's our transition diameter. Next up, depth diameter functions. And I'm going to summarize all of this in a table in a minute. But the depth diameter function can also give you a transition diameter, again, as was mentioned in the last talk. So this is the depth diameter data that we have for Pluto and Charon. As Jamie noted, there are diameter error bars. In this case, those error bars are smaller than the size of the marker. So they're shown, but they're not visible. But as I said, there are definitely those vertical error bars, and that is from the uncertainty propagation and variation. So these are our Pluto and Charon craters. Here I have colorized them, where green is going to be the ones that are classified as simple, and blue is going to be the ones that we classified as complex. Again, note, not everything could be classified. Even though if it was really big or really small, and I really wanted to say, okay, that's a complex and that's a simple just based on size, the whole point of this study is to assume that there is no size dependence a priori going in and to try to find that. So I didn't want to muddy the sample by doing that. So once we have these separated out, the question is, how do we fit these data? So this is, again, the statistics fantasia of how do we fit these noisy data. And there are lots of different ways to do it. A lot of people will just fit either a line to the log of the data or a power law. But you have questions like, there are anomalously deep craters. Should those be included or not? You have the question of, there are extra shallow craters that might have been modified even though we tried to not include modified craters. Should those be included or not? And so we have all of these questions of how do we do this? And so we came up with actually 4 different mechanisms for trying to fit our data. One was just doing the fits. Another was a method developed in the 1940s. Another was a Monte Carlo approach where we actually resampled all of our data based on those error bars, and we built up statistics, and we were able to then reject percentiles of data and do our fits that way. We also did a guess and check subtraction of possible fits, and we looked at those residuals to see what the best fit was based on when the residuals most resembled a certain probability distribution, like a Gaussian. Again, it's not entirely important to convey all of the different ins and outs of these methods. It's more, we used a lot of different methods to try to get at this problem and try to get that fit. Here are the results, and these fits go all over the place. And again, that's because we have somewhat noisy and limited data. And I think that you could look at any of these fits, and I'll blink sort of slowly back and forth between the data and the fits. And if you squint, you could say that any one of those fits is actually a somewhat reasonable fit to the data that we have. And so then the question becomes, well, what do we actually use? Because each of these have incredibly different transition diameters and very different slopes. So I guess the summary question was really, what is that depth diameter function? Our summary of the results before getting into how we picked and chose was, we looked at Pluto. Transition diameters were 8 to 12 kilometers, averaged really around 11.5 to 12.5. On Charon, it was a much larger range because it was somewhat noisier data. And the morphology transition was based on about 13.5 to 16 kilometers. That's where we had those smooth histograms. The morphometry transition, we decided we couldn't do. And that's because we decided that the Charon simple crater fits were unreliable. And that's because they are all way too steep. Based on every other body in the solar system where we have these fits, all of the simple crater curves have an exponent in that power law, have a power value of less than 1. Almost all of these fits are much greater than 1, which means that they're probably not right. Either that or Charon is unique in the solar system, which we considered a high bar for this kind of study when we do have somewhat noisy data. And so we decided to throw out the simple crater fits for Charon and say, we can't actually do a morphometry or a depth diameter based transition for those data. So once we actually weed out what data we believe and don't believe, and what fits we do believe and don't believe, and what transition diameter we think that we have, and again, that's summarized here, Pluto about 11 to 12 and a half, Charon about 13 and a half to 16 kilometers, they're actually somewhat similar. Pluto and Charon have a similar transition diameter. Charon is slightly larger, but they're within the noise of each other. They are within each other's error bars, or you could say effectively, they are the same, depending on how you understand error bars for the both bodies. Next, we can do a comparison of how does this compare with every other body in the solar system. This is based on a lot of different publications that I have not cited in this, but they're cited in our paper. The DOI is up at the top. When we plot our data, in this case, Pluto and Charon are shown as red on this plot, with other icy bodies shown in blue, we find that our data fit fairly well. So Pluto fits very well with Triton, has a similar surface gravity and similar transition diameter. Charon has a similar surface gravity to Ariel, Ceres, and Dione, and fits right in that area as well. And actually, from the last talk, Rhea is not around 5 kilometers, but could be much higher, and that would actually go really well with our data because it would match it quite well. So after all of this different analysis and all of these different how do we actually do this kind of analysis, we get a final data point that actually fits really well with the rest of the solar system. With that said, as I think, again, was also mentioned in the last talk, technique matters. If you use a different depth measurement technique, you will get a different result. And if you don't factor that in, somehow you will get various different results that you can't actually compare well. So on this plot, everyone pretty much used a different technique to classify the transition diameter. Everyone used a different technique to classify depth diameter ratios and measure depth values. And so I'll just put in a plug. Decisions have been made, but I don't know what they are yet. I did have an SSW proposal in this last round to actually try to redo this across the solar system to try to see how well do these values really compare once you use the exact same methods, the exact same data gathering type things, and the exact same analysis to really try to tackle this problem. And so what I'll do is I'll leave my wrap-up slides up, and I guess, are there questions in the chat? Or I'll say thank you for paying attention through my ramblings.
Thank you, Stuart. So I don't believe you can see the chat with your screen sharing, but we've got a comment from Paul Shank saying Oberon and Titania values are unreal. Best resolution is 3 to 5 kilometers. Yep. And then Clark comments, I'll grant Stuart's criticism of my thinking of flat floored as transitional rather than complex, but it still seemed that the quote overlap between simple and complex was much greater in the previous RIA talk compared with the Pluto Charon data. Wonder why, ...
I can't answer that question or comment. Yeah. So I'll just go back to this, that we do have all of these different morphologies that are indicative of different processes. And what you actually want to study is going to dictate what you actually use. So some people really are interested in that minimum, that absolute minimum where we start to see those transitions, in which case, again, part of this SSW proposal, and if it's rejected, we'll propose again, part of this SSW proposal was actually to try to parameterize this shape and see if we can provide a function such as fitting it to a sigmoid so that we can actually say for any given body what the range of transition diameters is, not only for different morphologies, but for a single morphology where you can expect to start to see at the 1% level versus the 50% level versus the 99% level. So I think it's it's classic work that I think needs to be revisited.
I was just going to add that, you know, flat floors are an interesting thing because they are also dependent on subsurface layering and all kinds of stuff and terrain properties. So they probably, it changes probably where you get a flat floor versus not a flat floor as you go into different terrains and stuff like that. So that's something I've noticed on the moon.
Yeah. I guess with no one else speaking for a moment, I'll say that on Charon, we do have a couple different terrain types, but fortunately, or unfortunately, depending on your perspective, we only had really good imagery and topography, and so crater data over one really specific area that's almost a single cohesive unit called Vulcan, either Planum or Planitia. I forget what it is now. We kept changing things and they switched, and it's confusing. But Vulcan, this area that might be an old cryovolcanic flow. And so that makes things a little bit easier on Charon. On Pluto, we have lots of different terrains, and we saw layering within crater walls. So it's a very confusing signal, but unfortunately, the number statistics are too poor to really try to tease those out, at least for these data.
Okay, we have a couple of comments here. Shangulik says, did you observe any complex craters with additional ring structures, such as impact basins, or could be interpreted as impact basins?
Not on Charon. On Pluto, there's at least one, Bernie. It's about 350 kilometers across. It definitely has very weird ring structure associated with it, rings that don't quite meet, that sort of are inset to each other. That's a weird one. There's also Sputnik, which is almost certainly was originally a peaked ring or ring, multi-ringed possibly basin, but it's filled with a glacier now. And so teasing out any rings right now is fairly impossible. Again, none on Charon.
Thanks, Stuart. We have a question. Thanks also from Sean. From Ankush, we have, what may cause small craters to have a flat floor?
Right, so one would not be formation-based, it would be infilling. Again, it's really hard to tease that out with these data, and it's even hard to tease that out sometimes on the moon and Mars when you have tens of centimeter pixel scales. So here, I tried to say that this is a bowl-shaped and not flat-floored because this, to me, looked like it was just mass wasting because it looked hummocky. It looked like there were multiple episodes of stuff that had fallen in, and usually flat floors are at least 50% the width of the crater, but again, that's a fully developed one, not necessarily a transitional one. Otherwise, I think the current thinking is that it's isostatic rebound is what gives you the flat floor. As you get to larger sizes, the material simply can't support that bowl-shaped transitional crater, and so it comes back up. But I am not a modeler, so I'm digging back in my memory for that.
Well, Paul Shank said generally flat floors are too large to be target related, and he suspects related more to rim debris. And in this case, he says that buries a small, poorly formed peak.